Alrighty, so we worked a lot on factoring and solving quadratics. Cool. Let's put it into play. Let's actually look at it work. So this lesson is quadratic functions in actions. We're going to see some of those things come to life. So when we're looking at this first example, it says during the school year, you are allowed to play online games for 1 hour each day. Your favorite game is Irritated Birds. Identify the key parts of this irritated bird's path. Okay, so if this is the irritated bird's path, it looks like we're looking at how long he's in the air and how high he is. So, or she, sorry, could be either. So it should be time on the x-axis and height on our y-axis. Okay. So identify the key parts. So let's start with the axis of symmetry. Again, because quadratics, they're beautiful parabolas that are all nice and symmetrical. So to find that axis of symmetry, I want to look for the highest point. Oh, well, we could really, it's 7.5. So what's half of 7.5? 3 3/4. So our axis of symmetry is x equals, because it is a vertical line, it is x equals 3.75. Cool? All right. So our x-intercepts, vertex. All right, so the vertex is also associated with our axis of symmetry. So our vertex is either the max or the min of our parabola. So in this case, our vertex is our max. It's the highest point of our parabola. So it looks like it's at 3.75, 14. So what does that mean in the context of the problem? Well, it takes 3.75, let's go with seconds, for the irritated bird, to reach 14 feet, meters, I don't know. It wasn't very specific in our scenario. All right, now let's look at the intercepts. So we have our intercepts at 0, 0. So our starting time. And the irritated bird lands after 7.5 seconds. I'm assuming seconds because minutes is way long time to be in the air. So 7.5 seconds. So notice our x-intercepts, the y value is always 0 because that's where it reaches the x-axis. So this tells us it took our bird 7.5 seconds to land. Now let's look at increasing and decreasing intervals. Okay, we've talked about these before. So our increasing interval, so how do we read a graph? Left to right. So first we are increasing. So remember, you read it left to right. So we are increasing from 0 to 3.75. So we read it along the x-axis. So when we are increasing when x is between 0 and 3.75. And then we are decreasing from that 3.75 until we land at 7.5. No, not 0. We said 3.75 to 7.5. That 3.75 should really not have the equal to sign since it is in both intervals, increasing and decreasing. It's our little pivot point. It's the max. It's the vertex. So increasing intervals from 0 to 3.75, then we're decreasing from 3.75 to 7.5. Awesome. So we're really just applying some things that we've already talked about. Now, what if we don't have a graph to analyze? What if we're just given an equation or a function? Well, let's try it out. So Ruby tosses a quarter off the Main Street Bridge into the St. Johns River. So the distance in feet the quarter is above the water is modeled by the function d of t. So the distance after time is negative 16t squared plus 96t plus 112, where t represents time in seconds. All right, makes sense. However, I am still going to give myself a little visual aid. Beautiful. Okay, so we said our independent variable, so it's d of t, so the distance relies on the time. So our time in seconds and the distance in feet. Cool. So I'm just sketching. Now, remember, if we are given a function, I'm going to rewrite that over here so I have some more room. Now, when I first introduced quadratics, I told you there were a couple things that we could learn just from looking at it in standard form. Okay? Now, C is always the y-intercept. So in linear, it was y equals mx plus b, that constant term at the end. Well, quadratics, same thing. It's that constant term at the end, c. So we are tossing the quarter from 112 feet up. So we toss the quarter up. What goes up must come down. Oh, that is definitely not perfectly symmetrical. I'm trying. No. All right, close enough. So what goes up must come down. Well, what also describes that shape is this negative 16. So when our a term is negative, that tells us that our parabola should be going down. It also tells me negative 16, so anytime that number is larger than 1, and I don't mean the negative just tells me whether it's smiling or frowning. So that the actual number itself tells me if it's a narrow or a wide parabola. This should be a really narrow parabola. However, time in seconds, so what I'm going to do is I'll probably spread out how I label the time. And I'm going to wait to label that in a second once I find some other key features. So first, it says, from what height was the quarter tossed? Well, that's our y-intercept. Nope, I want to stick with pink. Tossed from 112 feet. Okay, how long does it take the quarter to reach its maximum height? Okay, so we're looking for this max. We're looking for our vertex. Now let's go back up to the top. So part of our vertex is our axis of symmetry. So our axis of symmetry, if you can't look and say, okay, well, it's between 0 and 7.5, so that's perfectly in the middle. If it's something else, or if you're not given a graph to look at, you use the formula x equals opposite of b over 2a. That's going to help us find the x of our vertex, opposite of b over 2a. So let's go ahead and do that. X equals opposite of b over 2a. So what's the opposite of b? Well, let's find our b term. There's a, here's b. So the opposite of a positive 96 is negative 96 divided by 2 times a, negative 16. Okay, so negative 96 divided by negative 32 gives us 3. So our axis of symmetry is 3. So how long does it take the quarter to reach its maximum height? 3 seconds. Okay, so now what's the maximum height of the quarter? Well, the height is represented by d in this case, our distance. So the distance the quarter is from the ground, so if I know it's at 3 seconds, I'm going to find d of 3. So d of 3. Yes, you may use a calculator if it is necessary. So negative 16 times 3 squared plus 96 times 3 plus 112. All right, so always, always, always make sure we are following order of operations. So I'm squaring just the 3. The square is only touching the 3. So 3 squared is 9, and 9 times negative 16. Negative 144 plus 96 times 3. 288 plus 112. All right, so 288 minus 144. That leaves us with 144 plus 112. 256. Whoa. So she tossed that quarter 256 feet in the air. Granted, she started at 112. I would not call that a toss. I would definitely call that a throw. She chucked that thing. So it is a 256 feet is our maximum height. So you can use the single tick mark, or you can write out feet. Does not matter to me. Last piece. So those are the main pieces of a quadratic that we need to look at. Our y-intercept, all about the vertex. So if I wanted to write the vertex as an ordered pair, it would be 3, 256, and our zeros. So how much time does it take for the quarter to hit the water? Let's find out. So if I want to know where it hits the water, what is that? What's that distance or that height? 0. So that is why we are always setting this equal to 0. Okay, we want to know how long does it take it to hit the ground, or in this case it's off a bridge, so I'm thinking go in the water. All right, so that's why we set it equal to 0. We want to know when is the y, or when is the y 0. All right, so let's go ahead and factor. So I want to see if there's a GCF, because I definitely do not want to do negative 16 times 112. Whoa, that's huge. So let's see. All right, I'm going to try dividing some stuff by 16, see if that's a GCF. And perfect, it is. So I don't like my a term being negative, so I'm not just going to pull out a 16. I'm going to take out a negative 16. Okay, so when I factor out a negative 16, we're going to be left with t squared plus, oh no, we factored out a negative 16, so minus 6t and minus 7. Oh, nice. Now I just have something super small to factor. We can totally do that. Okay, so a is 1, a times c. So I have factors of negative 7 that give us negative 6. 1 and 7, so I want a negative 6, so 1 minus 7. All right, so my factors are, now if you haven't figured this out yet, if your t is 1 and I want to set up my factor, the only thing that will give me a t squared is a t times a t. And then we already know our factors are positive 1 and negative 7. Done, factored, cool beans. Okay, so what are the solutions? So what makes t plus 1 equal to 0? Negative 1. And what makes t minus 7 equal to 0? 7. So my solutions are negative 1 and 7. So Well, back to our question. How much time does it take for the quarter to hit the water? -1 seconds? No, definitely not. 7 seconds. So, it takes 7 seconds for the quarter to hit the water. Cool. What does that -1 represent? Well, if we took our graph backwards, because remember, parabolas are perfectly symmetrical, that's where it would hit the x-axis if it were to go backwards. However, in a real world situation, there's a lot of times where we're only going to take the solution that makes sense because we're not using the whole parabola. Our function rule has a parabolic. It follows those rules of a quadratic, so it has a parabolic shape, but we only use the pieces that make sense. Okay, I'm not going back in time. I'm not using negative time. And in this case, we're not going to go under the water. It would go under the water, but that would change the trajectory, so that wouldn't be a perfectly symmetrical anyway, because we would have a lot of other factors coming into play here. Cool. So you guys just took in a lot of information. So the three main things that we look at in a parabola, that starting point, which usually is the y-intercept in a real-world problem, the vertex, so that's also involves our axis of symmetry, so the time and the height, it consists of two pieces, and then our zeros. Where are we landing? Cool? All right, so you got a couple of problems to try on your own. Let's see how we do.